Okay, let's go ahead and get started. So, quiet, please. Thank you. Let's go ahead and get started. So today, what I want to do is begin our discussion of symmetries in quantum mechanics in earnest. So this discussion will take us approximately the next 2 weeks. We'll spend about a week on the theory of discrete symmetries, and then a week on the theory of continuous symmetries. Along the way, understanding their applications to all sorts of interesting problems in quantum mechanics. Let me begin, however, by just reminding you of a few things that we reviewed last time. So in classical mechanics, a continuous symmetry is a family of canonical transformations that is to say, changes of coordinates on phase space, which preserve the fundamental Poisson bracket, that the Poisson bracket of Q with P is equal to 1, which are generated by an observable, namely a function of Q and P, typically called G, which has the property, so first of all, the variation of some other observable under the symmetry generated by this generator G is proportional at linear order in the variation to the Poisson bracket of G with the observable under consideration. So this is the statement, this is another way of stating that G is the observable that generates the symmetry operation. So this is the variation of some other observable A under this symmetry. And this is the infinitesimal variation. So this is the term linear in G. Of course, as we will see, there can, in general, be other terms at the nonlinear level. And second, the Poisson bracket, this is the real definition of a symmetry, of our generator with the Hamiltonian of the system is equal to 0. And that implies two separate things. First, it means that G is a constant of motion, because G dot, the time derivative of G, is the Poisson bracket of H with G. So the generator G of a family of canonical transformations is a constant of motion. That's Noether's theorem. And the second consequence is that the Hamiltonian is invariant under the symmetry because the variation of the Hamiltonian with respect to the symmetry is again just the Poisson bracket of G with H. So that's equal to 0. So that's the statement of Noether's theorem. If you have a symmetry of the system so that the Hamiltonian is unchanged, then you have a constant of motion. In quantum mechanics, canonical transformations correspond to unitary operators on a Hilbert space. So a canonical transformation is promoted to a unitary operator. So a symmetry is in principle, it could also be an anti-unitary operator. Recall that we defined anti-unitary operators, I think, in the first or second lecture of this course. But it's some sort of linear operator which acts on the Hilbert space. So it will take a ket in the Hilbert space to some operator acting on that ket. I've denoted the operator U, thinking of the more common case where U is a unitary operator. But in general, it could be an anti-unitary operator as well. And there are actually two ways of thinking of the action of a symmetry in quantum mechanics. You could either think of a symmetry as the action of a unitary operator on the states in your Hilbert space, or you could think about the action of a unitary operator on observables, that is to say, operators on your Hilbert space. So just as there's a Schrödinger and a Heisenberg picture, where the unitary time evolution operator is thought of as acting either on the states or on the observables, likewise, when you consider symmetry transformations, you can think of them as either acting on states or on your observables. And we typically give names to these two pictures of how symmetries act in quantum mechanics. In the first case, we call that an active point of view if the symmetry operators act on the states, and we call it the passive point of view if symmetry operators act on the observable. So you may have seen these words in the context of classical mechanics when considering how things transform under rotations, for example. You can either take an active point of view where you rotate the vectors, or you can take a passive point of view where you rotate your coordinate system. And so that language, active versus passive, is inherited from that sort of classical intuition. So the first thing to note, so I remind you that the definition of a unitary operator is one that preserves the inner product so that if you take the inner product between two states, alpha and beta, then for a unitary operator, that is just the inner product of the action of U on the bra alpha, where it acts with the dagger, which is really just the definition of Hermitian conjugate, I suppose, times the action of U on the ket beta. So it preserves the inner product. And to see why this is the analog of a canonical transformation, which preserves the fundamental Poisson bracket, let's consider the point of view where we think of symmetry operations as acting passively, that is to say, on observables. Then you could imagine that you have some observable Q, which would describe, for example, the position of a particle, and an observable P, which is the conjugate momentum of the particle. And just using these symmetry transformation rules, we see that the commutator, so let's call this Q tilde and P tilde, then the commutator of Q tilde and P tilde is, well, if you just plug that in to the definition of the commutator, you'll see that all of the U's and U daggers cancel, and so we just get the commutator of Q with P, which is equal to 1. If that's not clear, just write it out, and you'll see that every time you have a U dagger sitting next to it, and so when you plug in the fact that Q and P commute to 1, you'll see that Q tilde and P tilde commute to 1. So this is the analog of the statement that you have some sort of transformation that preserves the fundamental Poisson bracket. Okay. And then in quantum mechanics, a symmetry is an anti-unitary or unitary operator U, which commutes with the Hamiltonian. So our goal for the next 2 weeks is to understand the implication of this statement that you have a unitary operator that commutes with the Hamiltonian for both the Hilbert space structure and the dynamics of various different quantum mechanical systems. We'll start with rather simple symmetries before moving on to a more complicated set of symmetries. Let me first make a few more statements about the general structure of symmetries in quantum mechanics, just in order to make the analogy with classical mechanics a little bit more precise. So for a continuous symmetry, which is to say a family of unitary operators which commute with H, we can consider an infinitesimal unit symmetry that is to say, we could consider a unitary operator which is very close to 1 so that it can be Taylor expanded order by order in some small parameter epsilon, so that it would take the form 1 plus I epsilon times some operator G plus higher order terms in epsilon. And then the fact that U commutes with H will imply that each one of the terms in this series expansion in order by order in epsilon must commute with H. So in particular, G is some sort of operator that commutes with H. And G, because of my choice of this factor of I in the way that I have written this expansion, is going to be a Hermitian operator. So just as in the classical mechanics case, we see that a continuous family of symmetries, if you think about them infinitesimally, if you think about the infinitesimal symmetries, will provide for you some observable G which commutes with the Hamiltonian. Are there questions? Did I make a mistake somewhere? Okay. So this implies, of course, that G dot in the Heisenberg formulation, G dot is equal to the commutator of H with G is equal to 0. So that is a constant of motion. And this, of course, is the quantum mechanical version of Noether's theorem. You have an observable, that is to say an operator, which is time independent, every time you have a continuous symmetry that you can infinitesimally expand around the origin. And just to make the analogy with classical mechanics a little bit sharper, you can remember that under this symmetry transformation, a general observable A is conjugated by this unitary operator. So if we plug in this infinitesimal expansion, this is A plus I epsilon times the commutator of G with A plus higher order terms, so that the variation of A to first order in this parameter epsilon is just I epsilon times the commutator of A with G. Is it A with G or G with A? It's A with G. Okay. I'm never quite sure. There might be some minus signs, up to minus signs. I have a PhD, so I can ignore all the minus signs. You don't have PhDs, so you'll need to understand what those minus signs are. Okay. I think, let's see. Let me work out the minus signs. It's actually A with G, isn't it? Okay. There might be some, there might be some conventional minus sign that I'm not keeping track of, which would make all of this a little bit sharper. No, actually, I think this is correct. Because remember, the rule, the quantization rule is that Poisson brackets become that commutators are 1 over I h bar times Poisson brackets. Okay, so there's a 1 over I there in that rule, which is why there's some relative sign. Why I'm writing the commutator of A with G instead of G with A. Okay. In the comparison between the classical and quantum mechanical formulations. Okay. So, in other words, the Hamiltonian, the variation of the Hamiltonian under one of these infinitesimal symmetries is equal to 0. Okay. So what is the fundamental utility, then, of these symmetries? The basic idea is that if you have a unitary operator which commutes with the Hamiltonian, these operators can be simultaneously diagonalized. So, in particular, if you have some energy eigenstate with eigenvalue En, then you could always act on it with this unitary operator that corresponds to a symmetry, and you'll find that this new state is also an energy eigenstate. With energy En. To see that, you just take H, acting on this guy, use the fact that the H commutes with U, so you can move H to the right of U, act on En to get a number, and move that number back through U to see that you found a new energy eigenstate. Thus, energy eigenstates are either invariant under U or are degenerate. Right? There are two possibilities. One is that U times En is just En, in which case your energy eigenstates are invariant under your symmetry. Or U times En is a new state with the same energy eigenvalue, so that you have some degeneracy. So the typical signature of an appearance of symmetry is the appearance of degenerate energy eigenstates. If somebody hands you a Hamiltonian and tells you what its spectrum is, and you happen to notice that there are a lot of energy eigenstates with exactly the same energy, then that's usually a hint that there's some sort of symmetry of the system which is responsible for that degeneracy. So, in developing the language and the study of symmetries, it's useful sometimes to use the mathematical language of group theory. And so, in my development of the subject of symmetries, I am going to use and introduce a little bit of the language of group theory. Now, this is not a class in mathematics, so the group theory that I'm going to use is very, very gentle. It's stuff that you could have learned in some elementary linear algebra class, although you may not have. But along the way, I'll introduce it just because that is the language that physicists use to discuss symmetries, and it's worth being exposed to this language a little bit. By the way, how many of you have know a little bit of group theory? Those of you, okay. Like, how many people know what a representation of a group is? Okay. Don't worry, that is not assumed in this class. And fortunately or unfortunately, the sort of group theory that you would learn in a math class is not the sort of group theory that we will need in a class like this. So even though you may have learned group theory in your math classes, chances are you haven't learned the sort of group theory that is relevant for the things that I'll be discussing in this class. So those of you who don't know any group theory, don't worry. your colleagues who do know group theory are just as at a loss as you are. They just don't know it yet. Okay. Good. So, what is a group? A group is a set equipped with a multiplication rule So let's call this set G. No, let me not call it G. I've already used G. Let's call it, what should I call it? God, I really want to call it group G. Let's call it gamma. Gamma's pretty close to G. Okay. Which has the following property. First, if you have two elements in your group, then you can multiply them together to get another element in your group. Second, there is a special element of your group, usually denoted 1, such that 1 times an element is just equal to that element, independent of whether you multiply on the left or the right. And third, for each element of your group, there is an inverse such that G times G inverse is G inverse G is that identity element. And given a set of symmetries, that we'll call gamma, the basic rules of quantum mechanics tell us that these form a group. So a set of symmetries of a given system Why? Well, you take two unitary operators that commute with the Hamiltonian, and their product will commute with the Hamiltonian. So that says property 1 is okay. There's also, so 1 is, of course, the trivial symmetry operation. 1 commutes with everything. Particular commutes with the Hamiltonian. So that means that among the set of symmetries of your system, you have the trivial symmetry that does nothing, satisfying property 2. And given a unitary operator, it's if the unitary operator commutes with a Hamiltonian, then so does its conjugate, so does its adjoint. So that means that property 3 is satisfied, because for unitary operators, their inverse is their adjoint. Okay. But the basic idea is that it is often, is that many different systems often have the same set of symmetries. And so, for that reason, it is often useful to think of a set of symmetries as an abstract group. That is to say, just as some set of elements that obey these 3 principles that I have outlined. And a Hilbert space with the symmetry as a quote-unquote representation of this group. Now, what do I mean by this word representation? Well, what do we mean? A representation of a group gamma is, formally speaking, a map, or, well, let me try and not say this too mathematically. So a representation of some group is a Hilbert space H, and an association of a unitary operator, or let me say this slightly differently. Sorry, I'm not saying, I want to say this as clearly as possible. And a map rho which defines a unitary operator for each element of gamma. So, given a G in gamma, we have rho of G is a unitary operator. So, is a unitary operator on our Hilbert space with the property that rho of G1 times G2 is equal to rho of G1 times rho of G2. So all that means is that these unitary operators obey the same group multiplication law as our group gamma. So I haven't actually said anything. Okay. All I've said is that we think of symmetries as a group, and we can specify an abstract group of symmetries that we would like to act on our Hilbert space. And what we mean by that is that we have a set of unitary operators acting on our Hilbert space that respect this group multiplication law, that obey this group multiplication law. Why is it useful to use this sort of formal language? The reason that it's useful is that the existence of a symmetry then constrains the possible Hilbert spaces. And, of course, the possible Hamiltonians. So, for example, let's say that we're looking for systems with rotational symmetry. Then the rotations in three-dimensional space form a group. Okay. There are many ways of thinking about this group. So if you saw Euler angles in your classical mechanics class, did you guys see Euler angles? Yeah. Then that's a way of parametrizing the various different rotations in three-dimensional space in terms of three angles. Okay. And you can think of the rotations as some abstract group. And then you can look for Hilbert spaces on which these rotations could act. Meaning that you could look for Hilbert spaces with the property that there are unitary operators, one for each rotation, that act on this Hilbert space. And if you do that, you'll find that there are an infinite number of possible such Hilbert spaces that are labeled by a number j, typically referred to as the spin of the representation, and that this j is a half integer. So the existence of a rotation symmetry implies that the possible spin of an object is half integer. Okay. So that's one example of this symmetry language at work. So in Newtonian physics, there are more symmetries in the world than just rotational symmetries. For example, there's also what's known as Galilean symmetries. Have you guys seen this language before, Galilean symmetries? So, we're going to discuss Galilean symmetries in more detail. But basically, this is the symmetry principle of Newtonian physics that tells you that not only is physics rotationally invariant, but if you go to a frame which is moving at constant velocity, the symmetries, the laws of physics are unchanged. If you perform an experiment in a classroom at rest, you'll get the same result as in a classroom that's inside a train that's moving at constant velocity. And Galilean symmetries, the existence of a Galilean symmetry, implies that the possible Hilbert spaces are not labeled by one number, which would be the spin J in the case of rotational symmetry, but rather by two numbers, typically referred to as J and M. J being a half integer again, being the spin of the representation, and M being the number that we commonly denote as mass. Okay. So for example, the Galilean symmetries of Newtonian physics are why it is that objects have a spin and a mass. Okay. So, and likewise, if you generalize this to Lorentz symmetry, as you would in special relativity, life gets a little bit more complicated. There are representations associated with massive particles, which are again labeled by spins, but now not by mass, but by some energy momentum, okay, which is the relativistic version of energy momentum. And there's also a special family of representations associated with massless particles. And there are other sorts of variables that are like spin, but not quite spin, known as helicity, that we use to parameterize those representations. Okay. So you can see, just based on the symmetries of nature, you can understand why it is that we parameterize objects with different physical quantities. So the reason why objects have a spin, which is a half integer, is that our world is rotationally invariant. And the reason why objects have other fundamental properties is due to other symmetries of nature. Okay. Galilean invariance, Lorentz invariance, and so forth. Likewise, for example, the fact that electromagnetism has gauge symmetry is what is responsible for the fact that we label states by a charge. Okay. And so this general group theory language, this language of representation theory, is really what is responsible for a lot of our understanding of the basic properties of matter. So another example would be that it was observed, in the reason why we know that the various theories of particle physics are governed by certain symmetries is that we observed that there are certain conserved quantities in particle interactions, things that people called isospin and color and things like that, and then people built up the corresponding symmetries. You hear about the symmetry group of the Standard Model of Particle Physics a lot. They built them up by observing these various different new conserved quantities in particle physics interactions. Okay. So there's a beautiful sort of history of physics where, which really goes both ways, where people observe symmetries in nature and then work out from that the corresponding consequences. And then there's the alternate history where people observe conservation laws, they observe degeneracies in the eigenstates of Hamiltonians, and then postulate from that a symmetry principle underlying it, which they then use to make further predictions. Okay. So this is really one of the basic strategies that we use in physics. So for example, in condensed matter physics and in materials physics, the basic strategy that one always uses essentially in understanding the dynamics of some system is you start by postulating the set of allowed symmetries of the system. So for example, if you're studying a crystal then the symmetries might be the group of crystalline lattice symmetries associated with crystal structure, and then you would use that to constrain the possible physics that would result. Okay? And we'll see a simple example of that, probably not this class, but possibly later in this class, when we discuss the band structure of metals. But let me pause here and see if there are any questions. So, as we proceed over the next week or two to understand various different sorts of symmetries, I'll gradually introduce more and more of this group theory language. Okay. I could have structured this class by giving an entire lecture or two on abstract group theory before diving into examples, but I think rather a better thing to do is to teach by way of examples, work through gradually more and more complicated sets of symmetry operations, and in doing so introduce some of the language associated with symmetries and group theory and quantum mechanics. Any questions? Okay. So let's start. Yes?
What exactly is the map that you're talking about, let's say for spins?
Well, for spins, we're going to beat that example to death. Okay. So what do we mean for spins? Well, say that you have a rotation symmetry, okay? Then you have some generators of rotation symmetries, Jx, Jy, and Jz. And for a spin 1/2 symmetry, you associate those with the Pauli matrices, okay? So there's a map which takes Jx to the Pauli matrix sigma 1, Jy to the Pauli matrix sigma 2, J3 to the Pauli matrix sigma 3. So that that's a great question. A specific example of this map will be the one where you think about the abstract rotation around the x-axis as corresponding to the 2x2 operator sigma 1. Okay, 0, 1, -1, 0.
And is there other representations?
And there are other representations. If you want to describe a spin 0 particle, then Jx, Jy, and Jz all map to the trivial operator 1. Okay. If you want to describe a spin 1 representation, then they map to 3x3 matrices. Okay. And this is something that we'll work out in glorious detail next week at some point. So that's a good example, and we'll see lots of other examples as we go along. Good question. Okay. Let me consider one of the simplest possible symmetries. Okay. So I'm going to start by discussing discrete symmetries rather than continuous symmetries. So the simplest possible symmetry is parity symmetry. Excuse me. So the parity symmetry corresponds for reflection symmetry is a unitary operator pi people sometimes call it P, but I'll be using P later on in this class for something else. And I guess we also use it for momentum. So it's the unitary operator pi. Well, first of all, it commutes with the Hamiltonian. But really, its defining property is that it takes x to minus x. Okay. That's what we mean by a reflection symmetry. And in quantum mechanics, that means that the action of parity on the observable x would be equal to minus x. Here, I'm thinking about a particle moving in one dimension. Of course, you could think about particles moving in more dimensions. So if you have a particle moving in 3 dimensions, there are really 3 sort of parity operations that we could consider. One which takes x to minus x, y to minus y, and z to minus z. And you could also consider combinations thereof. Or, rewriting this, the anti-commutator of pi with x is equal to 0. Pi x plus x pi is equal to 0. And note that pi necessarily squares to 1. because you reflect twice and you get back to the same point that you started at. So pi inverse, which is equal to pi dagger, because the operator is Hermitian, unitary, is also equal to pi. So parity is rather unique among all the various sorts of symmetries, in that it is both unitary and Hermitian. How does parity act on the Hilbert space of a theory? Well, parity anti-commutes with x, so that when you commute it through x, you don't get pi x equals x pi, but rather pi x equals minus x pi. So if x is, I'll put my hats here. I'll denote operators by hats in this equation just to keep everything simple. So if a state x is a position eigenstate, then you act on it with parity. And what do you get? Well, let's see what happens if you act on it with x. Using our anti-commutation rule, this is minus pi x hat acting on x, which is just x acting on x. So it's equal to minus x times pi x. So if you take a particle at position x, you act on it with the parity operator, and you get a particle at position minus x. Okay. Technically, I suppose it could be position minus x times a phase, but we're going to just choose that phase, so choose the definition of the parity operator, or the normalization of the parity operator, so that phase is equal to 1. Okay. Now, since pi squared is equal to 1, its eigenvalues are plus and minus 1. And since pi can be commutes with the Hamiltonian, pi and the Hamiltonian can be simultaneously diagonalized, meaning that all of the non-degenerate eigenstates of the Hamiltonian can be taken to have parity eigenvalue either plus or minus 1. What does that mean for the wave functions? Well, let's say that you have a state which has a parity eigenvalue plus or minus 1. Then what does that mean for the wave function of the state? Well, let's compute its wave function. So that is equal to plus or minus psi of x, plus or minus the wave function psi of x. Or if you take this parity to act on that x, that is equal to psi of minus x. So parity eigenstates with eigenvalues plus or minus 1 have wave functions which are even in the case of plus 1 or odd in the case of minus 1 under the reflection x goes to minus x. And energy eigenstates are either parity eigenstates or come in degenerate parity pairs. So, for example, if you have some potential which is symmetric under x goes to minus x, then if the eigenstates are non-degenerate, they are either even or odd under x goes to minus x. So a typical example might be the simple harmonic oscillator, where the states with n excitations, the nth eigenstate, has parity minus 1 to the n. So the ground state is even, the first excited state is odd, and so on and so forth.
Do you mean by degenerate parity pairs? Do you just mean you can construct?
There are two states which are have the same energy eigenvalue that are related by the action of parity. Question?
Just a bit higher.
Yes.
Should it be the top right plus or minus x inside the graph?
In which here? I'm sorry, plus or minus x. Thank you. No, I'm sorry, minus x. Right. Because what is the point? The point is that pi acting on x is equal to a state minus x. Okay. The question is psi of x equal to plus psi of minus x or minus psi of minus x? The definition of an even state is one where psi of x is psi of minus x. So in the case where you have a plus sign here, psi of x is equal to psi of minus x. When you have a minus sign there, psi of x is equal to minus psi of minus x. That's what we mean by an even or an odd function under x goes to minus x. So let me introduce a little bit of terminology. And this is terminology that's not special to parity, but is a general terminology that we use whenever we have a symmetry. So we say if the system is in a state which is not invariant under all the symmetries, of a system, we say that the symmetry is broken. So if you have a quantum system where the Hamiltonian has some symmetries, but the system is in a state which is not invariant under the symmetries, then you would say that the symmetry is broken. So in the case of parity, the odd parity eigenstates would be ones where the parity symmetry is broken. Often, the ground state of a system is invariant under the symmetries. For example, in the harmonic oscillator, the ground state was symmetric rather than antisymmetric. So it turns out that for parity, as you're going to prove, I believe, on a problem set, for generic potentials, which are symmetric under x goes to minus x, the ground state is always going to be even. However, if the ground state of a system, the lowest energy state of a system, is not invariant under the symmetries, we say that the symmetry is broken, and in particular, we say that it is spontaneously broken. The theory of spontaneously broken symmetries is incredibly important. Superconductivity can be understood as a spontaneously broken gauge symmetry. The Higgs mechanism, which describes the origin of masses in the Standard Model, also comes from a spontaneous breaking of one of the gauge symmetries of nature. So cases where the ground state is not invariant under a symmetry are very, very interesting. Question?
Yeah. Going back to Parity, previously the eigenstates are either Parity eigenstates or different pairs.
Yes.
Then you give the example if the VFX goes to VF minus x, if eigenstates are non-degenerate, they are even or odd.
Yes.
So
Right. So if the eigenstates are non-degenerate, then they can't come in degenerate parity pairs, meaning that they have to be either even or odd. Okay. Right.
right.
Let's think. Okay. Should I go through that in a little bit more detail?
Can you give an example in terms of if n equals 2 5%?
I guess. Okay. I mean. Here, let me explain that statement in a little bit more detail. Okay, so this was just a bit of an aside. Okay. So let's say that you have some eigenstate with energy E. Okay. So H of E is just a number. Then you can consider parity acting on that state, and you'll find, because H commutes with pi, that it's an energy eigenstate with the same eigenvalue. So it can either be your original state that you started with. So, for example, if the Hamiltonian is non-degenerate, meaning that all of the eigenstates of the Hamiltonian have distinct energies, then pi of E has to be equal to E. Okay? In principle, it could be a phase times E, but you can always just choose your normalization so that phase is 1. That's just saying basically that pi squared is 1 instead of equal to a phase. And so E is a parity eigenstate. Okay. I guess in general it could be some phase, but we're choosing that phase to be real, so it'll be either plus or minus 1. So that pi squared is equal to 1. Yes. So I guess I'm not quite sure what your question is.
Yeah, what I
Do you want an example where you do have a degeneracy?
what I want to understand is the point of your example, because how is that a different thing from the general case used above? You see that
It's just a restatement of. All I'm doing is this sentence is just a rephrasing of that sentence.
okay, but
I just wrote some of the words in different order. Yeah.
Or any other eigenstate, right?
Yes?
So what does your requirement v of x will v of minus x?
If v of x is equal to v of minus x, then your Hamiltonian is parity invariant, is commutes with parity. If v of x is not equal to minus x, then your theory doesn't have parity symmetry.
Oh,
Right? Because the commutator of h with p takes x to minus x. So if v of x is equal to minus x, then h commutes with pi. Okay. But if v of x is not equal to v of minus x, then h doesn't commute with pi. Sorry, was that the question? Okay, good. Sorry, maybe I should have said that a little more straightforwardly. Good. Are there other questions? Yes.
Later on, if the symmetry is broken in the ground state, it exists in higher energy states?
Absolutely. Okay. This is what we do at the LHC. Okay. The ground state of nature that we all live in is one where one of the symmetries of the Standard Model is broken. But if you create, in the very early universe, for example, when the universe was at very high temperature, or in the LHC, when you collide these objects together to make a big blob of energy in a very small space, you're in some very high energy state where that symmetry is effectively restored. Good question. Yeah, so the theory of spontaneously broken symmetries is one that we won't really get into in this class. Maybe I'll see what our schedule looks like. Maybe if I can give a lecture on its application, for example, to superconductivity, which is really not so complicated. Superconductivity can be understood in exactly the same way, that there's some sort of Bose-Einstein condensate of some electron pair, of what are called Cooper pairs. So electrons are fermions, so they can't form a Bose-Einstein condensate, but if they pair up according to some interaction, they can be bosons, they can condense, and that condensation spontaneously breaks the gauge symmetry of electromagnetism, and in precisely the sense that I've described here, and that breaking is what's responsible for superconductivity. So, I mean, the theory of symmetries and the theory of how is really, I mean, probably the most important tool that we have as physicists for understanding the world. Okay. I think that's not an exaggeration. Okay, good. Let me give you one other application of parity, okay, which is a very simple version of a much more general phenomenon. So let's consider two states. I'll call them alpha and beta. Let's consider these to be states with definite parity. And consider some observable A, which also has definite parity. Okay. What do I mean by that? Well, what I mean is that alpha and beta are parity eigenstates, so that if you act on them with the parity operator, you'll just get a number that I'll call epsilon sub alpha and epsilon sub beta, and also that if you act with parity on the operator A, you'll also get just a number times A that I'll call epsilon A, where all of these numbers are just plus or minus 1. Yes?
Should you be getting epsilon A alpha?
I'm sorry. Of course. Thank you. Yeah. Okay. So let's then consider the matrix element of A between the states alpha and beta. So using the definition of epsilon A, alpha and epsilon beta, just using the fact that beta is epsilon beta times pi beta, and alpha is epsilon alpha times pi alpha. I'm using the fact that epsilon alpha are plus and minus 1 here, so you can just move them onto the other side of these equations. We can then use the fact that pi A pi is epsilon A times A. And what we see is that this matrix element is equal to itself times the product of those three numbers, epsilon alpha, epsilon beta, and epsilon A. So what does that mean? That means that this matrix element is equal to 0 unless epsilon alpha, epsilon beta times epsilon A is equal to 1. So without doing anything at all except noticing that there's a symmetry, we automatically know that half of the matrix elements of any given operator have to be 0. For example, if we have a parity odd observable and we compute its expectation value in a parity even state, then it's equal to 0. Likewise, the matrix element of an odd operator between even and odd states is 0. And the matrix element of an even operator between even and, I'm sorry, that's not true. The matrix element of an odd operator between two parity odd states is equal to 0. And the matrix element of an even operator between an even and an odd state is equal to 0. So, for example, in the simple harmonic oscillator, if you want to compute the expectation value of the 17th power of x in the 14th energy eigenstate, that's equal to 0. Okay. Now, in fact, as you might guess, this basically, in the case of the simple harmonic oscillator, boils down to the fact that this expectation value is found by computing an integral of some wave function times an operator, and the fact that it's 0 will just follow from the parity symmetry of that integrand. So, for example, the expectation value of x in the ground state of the harmonic oscillator is 0, just because the integral dx of x times e to the minus x squared is the integral of an odd quantity, and so that has to be equal to 0 when you integrate from minus infinity to infinity. And this rule that I'm putting in a box up here is an example of what is known as a selection rule. And it's sort of a version of Noether's theorem for discrete symmetries. Even though discrete symmetries aren't generated by observables, because you can't consider an infinitesimal discrete symmetry, they still have constraints of the dynamics of the system. And that's visible through these sorts of selection rules. Okay. So, for example, when considering transitions between various states in the hydrogen atom, these selection rules can be very important for understanding which lines can appear in the spectrum of hydrogen, and so forth. Okay. Any questions? No questions. Okay. Let me mention one more property of parity. So, one useful thing to consider is how operators transform under parity. So we saw that x goes to minus x, and likewise, if you have an object with a given momentum, and then you look at that object in the mirror, it will appear to have opposite momentum, meaning that momentum goes to minus momentum under parity. That's clear, I think, in classical mechanics. X goes to minus x means velocity goes to minus velocity, so momentum goes to minus momentum. And for vectors, if you consider an object moving in 3 dimensions, you'll find similarly that the vectors will pick up a minus sign when we perform this parity operation. One of the things that's interesting, however, is that if you consider the angular momentum, which is the cross product of x and p, then under parity, that will not pick up a sign. Why? Well, x picks up a sign, p picks up a sign, and the product of 2 minus signs is +1. Indeed, if you take a rotating top and you look at it in a mirror, the angular momentum vector of the top is the same in the mirror. It's not reversed in the mirror. Okay. And so, We usually have a special name that we associate to vectors of this sort. Okay. So x and p are parity odd vectors. The name that we give to a parity odd vector is very special. We call it a vector. Okay, that's a joke. But the angular momentum, for example, is a parity even vector. And we usually call that a pseudo-vector. The use of the word vector in this context, what do we mean by the word vector? A vector is a set of three quantities that transform in a particular way when you do a rotation. You multiply them by the rotation matrix. And so when I use the word pseudo here, what I'm saying is I'm not just telling you how this thing transforms under a rotation, I'm also saying how it transforms under a reflection. So when I distinguish between a normal vector and a pseudo vector, I'm telling you, in addition to how it transforms under a rotation, how it transforms under a reflection. And remarkably, there's a similar set of considerations that occur with scalars. So, for example, the scalar x squared is a parity even scalar. And the name that we give to parity even scalars is scalar. Okay. But, for example, if you take the spin of a particle, dot it into its position. So this would be an example of the interaction term for a particle in a magnetic field, for example. Then spin is going to be parity even, just like angular momentum. So that's some parity odd scalar, which is known as a pseudoscalar. Yes, it's exactly reversed. Why? It's because usually you think of position and position squared as the standard vectors and scalars. Pseudovectors and pseudoscalars are unusual. You may have encountered them in your electromagnetism class. Have you seen them in electromagnetic waves? Like the pointing vector, I don't remember. Yeah. But you will encounter them in electromagnetism, for example. Okay. So that ends everything I wanted to say about parity. I have a few minutes left, so let me go through another example of a very simple discrete symmetry, which is the permutation symmetry of identical particles. So let's consider two identical particles. Maybe I should pause and see if there are any more questions about parity. Yes? Yes. How I derive the selection rule? Okay. So I have this matrix element, which has to be a number times itself. Okay? So divide both sides of that equation by the matrix element alpha A beta, and you see that epsilon A, epsilon beta, epsilon alpha, epsilon beta, epsilon A is equal to 1. Okay. However, you certainly could consider the case where that's not 1. And the only way that that equation then could be sensible is if it's saying that 0 equals 0. Good. Other questions? Yeah. Okay, let me spend the last few minutes of this class talking about one other very simple sort of symmetry. Consider two identical particles, each of which is described by a Hilbert space H, so that the total system containing those two particles is the tensor product of H with itself, whose basis is given by the tensor products So I'll use the subscript 1 and 2 to denote the two different Hilbert spaces of the first particle and the second particle, where K is a label of basis elements for the Hilbert space of a single particle. And if the two particles are identical, then that means that the basis element K1, K prime 1, K2 is physically indistinguishable from the state where the first particle has momentum K and the second particle, the first particle is in a state K and the second particle is in the state K prime. So what does that mean? It means that the permutation symmetry P12, whose action is defined by its action on these basis elements as just the operator which interchanges the two states, commutes with the Hamiltonian. The statement that we have two identical particles is the statement that the Hamiltonian commutes with this permutation operator. And just as with parity, P12 squared is equal to 1, so that the eigenstates of the permutation symmetry have eigenvalue plus 1 or minus 1. Now, for n identical particles, there are n factorial possible permutations. The n factorial possible ways that you could permute the various particles. And if the particles are identical, then they will all be symmetries of this system. And it's a mathematical fact, and one that I won't bother to prove for you, but which you can probably justify to yourself, at least in some simple examples, that all permutations are products of flips Pij, which interchange the ith state with the jth state. Have you guys seen that before? In math classes, you may or may not have seen it before. Okay. It's just a fact about permutations. Work it out for the permutations of 3 particles if it's not clear. Just work out how it all works. It's pretty simple. Okay. And it's just a fact, and one that can be proven, but I am not going to prove it to you, that in nature, all particles are either even, in which case we say that they're bosonic, or odd, in which case we say that they are fermionic under permutation, under one of these flips where we interchange the ith and jth state. So if you have a system of n bosons, and you act with this permutation, then you'll find that P has eigenvalue plus 1, whereas for a system of n fermions, you'll find that the action of P gives you a minus sign. Okay. And it is a second fact And an incredibly interesting and highly non-trivial fact that bosons have integer spin and fermions have half-integer spin. I can't spell the word half. If I did, fermions would have half-integer spin. Recall that the spin of the particle is related to the way that it transforms under rotation. So, a priori, this is an incredibly weird fact that the way that particles transform under rotation is related to the way that they transform when you interchange them. Okay. But, and in non-relativistic physics, this is not something that can be proven. This is just an experimental fact. However, it turns out that it is actually a consequence of special relativity. In particular, it's a consequence of the Lorentz invariance of nature. And indeed, if you think of the group of Lorentz transformations, the set of Alboost and rotations, then the fact that bosons have integer spin and fermions have half-integer spin follows from the topology of the Lorentz group. Okay. So that's something that is beyond the scope of this class. It's also beyond the scope of whatever next class you would take in this subject. But it's a beautiful and interesting mathematical fact. And a mathematical fact that has profound and important consequences for nature. I should mention, as an aside, that this is a consequence of the properties of Lorentz transformations in the number of dimensions that we live in, that is to say, 3 space and 1 time dimensions. But in lower dimensional systems, such as if you were studying electrons confined to a plane, as would appear in condensed matter systems, such as in the fractional quantum Hall effect, the effective excitations of the system can have more complicated statistics. That is to say, they can have more complicated transformation rules. Just as a bit of nomenclature, this is referred to as statistics, the statistics of a particle, and this is referred to as the spin statistics relation. And the possible statistics of a particle in lower dimensions can be more complicated. So it can take any sort of value under a permutation. So we call these excitations anyons. And if you take 2 anyons and you interchange them, you can actually get a phase times an anyon. Okay. And these are actually observed in nature. Now, they're not observed as fundamental particles, because fundamental particles live in our 3 plus 1 dimensional universe, where the spin statistics theorem holds. But if you look at condensed matter systems, such as systems of electrons that are confined to a plane in some sort of material, some very thin material, for example, you can look at the excitations of that material, and you can move these excitations around each other to interchange them, and you'll see that you'll pick up a phase. Okay, so anyons are observed in nature. And indeed, probably the best hope that we have for building a quantum computer is to build it out of these anyonic excitations of, for example, some fractional quantum Hall system or something like that. So these are actually, I expect that in the next decade or two, we'll be hearing more about anyons in the news, at least I hope so, because there's all kinds of really fascinating physics you can do with them that you can't do with bosons or fermions. I should stop here. Sorry, I went over a little bit. Maybe, are there any questions? A quick question?
So in this case, the permutation operator is not why is that?
Yes, the permutation operator is not Hermitian. Okay. Remember that I know, so the permutation operator doesn't square to 1. Okay. It's very funny. But it's a true fact.
It doesn't square to 1? Or?
That's right. It doesn't square to 1. Okay. I'll see you guys on Wednesday. When you're